Hello and welcome to the Direct Compute lecture series. In this presentation, we're going to talk about integration of compute shaders with the graphics pipeline. My name is James Fung. I'm with Developer Technology at NVIDIA. Here's an outline for the talk today. First, we're going to cover Direct 3D Graphics Pipeline. We're going to look at vertex, geometry, and pixel shaders inside the pipeline. Then we're going to talk about how to use compute shaders to help in data visualization, using them to process 2D arrays, particles, or other data. Finally, we'll look at a few direct compute examples. In particular, we're going to look at an image processing example, an N-body astrophysics simulation example, and an FFT ocean water simulation example. Let's look at the graphics pipeline over the last 20 years. Previously, the graphics pipeline was a fixed function model. However, now we have things like vertex shaders and pixel shaders, showing that the graphics pipeline has become more programmable and flexible. The DirectX 10 pipeline added a geometry shader, stream output, shader model 4.0, 8 multiple render targets, render target arrays, and texture arrays. The DirectX 10 pipeline is shown here, where a geometry shader is performing per primitive processing. For each input primitive, the geometry shader produces one or more output primitives of the same topology or a different topology, but all output a single topology. So for instance, you can have a triangle in and pointer lines out. The geometry shaders depart from the one-to-one processing of vertex and pixel shaders. This allows for data amplification and allows you to have dynamic geometric complexity in the geometry shader. So how does this all work together? Here's an overview of Direct3D 11 pipeline. And as you can see, it's basically the Direct3D 10 pipeline with the addition of a compute shader and the addition of 3 new stages that support tessellation. In the diagram, the square boxes are fixed function portions of the pipeline, and the rounded boxes are the programmable shaders. Compute shaders are a new shader type that's supported in Direct3D 11, and these are designed for general purpose processing. Using a compute shader doesn't require a separate API. It's integrated with Direct3D. And compute shaders share memory resources with graphics shaders. In a compute shader, the thread invocation is decoupled from input or output domains. This means that a single thread can process many or one data elements. In a compute shader, the data can be shared between threads. Additionally, compute shaders support random access memory writes. In the hardware, there's a D3D 10.x hardware support that provides a subset of the Direct3D 11 shader functionality. Both NVIDIA and AMD have hardware to perform this. It provides support for raw and structured buffers. Direct3D 11 supports a Compute Shader 5 profile, and that hardware adds more features. In particular, it adds UAVs, double precision, atomic operations, and append and consume operations, in addition to tessellation. The Compute Shader 4.x is a shader model, and it's based on the Vertex Shader 4.0, 4.1 instruction sets. But Compute Shader 4.1 includes Direct3D 10.1 features, such as texture cube arrays. You can run Compute Shader 4.x on devices that return true for the caps bit, compute shaders, plus raw and structured buffers via Shader 4x. They also add Compute Shader inputs, thread ID in group, thread group ID, and thread ID in group flattened. What does Compute Shader 5 add to Compute Shader 4x? It adds atomic operations, append consume operations, typed UAV access, double precision, and also the dispatch indirect call. Some other differences are that in Compute Shader 4x, only a single UAV is allowed. This isn't a huge restriction in practice, since you can use a UAV and have a single UAV and have different segments inside it to simulate multiple UAVs. Thread group dimensions are limited to 65,535, and the Z dimension must be 1, meaning no 3D grids. Thread group size is restricted to a maximum of 768 threads total. Finally, thread group shared memory is different on DirectX 10.1 and Direct3D 11. Direct3D 10.1 supports 16 kilobytes with restricted memory addressing, whereas Direct3D 11 supports 32 kilobytes with fully addressable memory addressing. So what are some performance recommendations for direct compute? Well, when you're mixing compute and rendering, the transitions between the compute shaders and the rendering are expensive, and so you'd like to reduce them. So for instance, you'd like to perform all your compute shaders before you move to rendering. With compute shaders, the thread group size is essential for good performance. In general, scattered read and writes are inefficient, and you'd like to instead use contiguous writes. Because you have thread group shared memory in a compute shader, you can use a thread group shared memory for scattered address support. So for instance, you can read in a contiguous memory into your shared memory, perform your scattered access on your shared memory, and then write back out a contiguous segment. What are some applications of the compute shader? Some applications include image processing for performing reductions, say for tone mapping, or performing blurs or image compression. Compute shaders can also be used for physics. You can use them for particle systems or fluids, or collision detection. You can also use compute shaders for AI and do pathfinding, for instance, on the GPU. In animation, compute shaders can be used to provide advanced skinning and deformations. Let's look at some examples. Let's start with an image processing example. In our image processing example, we're going to look at a rolling box filter. What we're going to do is our rolling box filter is going to compute a box filter of any size radius for constant cost. As we'll see, it only requires 2 adds and 1 multiply per pixel. In our implementation, we're going to take advantage of the scattered writes provided in the compute shader. Our example uses 1 thread per row and per column in the image, and we're going to do a separable convolution essentially. In this case, our parallelism is limited by the image size. For each step, an incoming new pixel is added and an outgoing pixel is subtracted, that leaves a window. This operation can be iterated in order to approximate a Gaussian blur. A compute shader box filter is faster and more efficient than a pixel shader, and it's not possible to do this implementation of the rolling box filter using traditional pixel shaders. Let's look at how the algorithm proceeds. For the first pixel that the shader computes, there's a little bit of overhead where it needs to read in the entire filter mask area and perform a computation in order to sum them up. However, for the next pass, it can use the sum that it computed previously, and all it needs to do is load 1 new element that enters the window and add that to the sum, and then subtract the element that left the window. Similarly, for the other pixels in the image along the row, it can perform the same operation. It only needs, again, to add in the pixel that enters the window and subtract the pixel that leaves the window. Here we see some code for the vertical pass of the box filter. In this code, we have 1 thread running per column. This compute shader is using input from a texture and writes the output to a structured buffer, UAV. Because the second start also needs to read from a texture, inside the host code, we'll need to make a copy of this output UAV and send it to a texture as input to the next pass. This is a code showing the second pass, the horizontal, of the rolling box blur. Here we have 1 thread running across each row. Again, the compute shader reads from a texture and writes to a structured buffer. Note also that the image is transposed. This is in order to keep memory writes coalesced, and that gives us the best performance. Structured buffers are a new type of buffer that contain elements of a structured type. To create a structured buffer from the API, set the D3D11 bind unordered access in the bind flags so that it can later be bound as an unordered access view. Note that the D3D11 bind shader resource flag can also be set, and so the buffer could be also bound as a shader resource. Unordered access views, UAVs, are a new type introduced in Direct3D 11. UAVs allow unordered read-write access from multiple threads. On D3D 10 hardware, UAVs are only possible from compute shaders, but on D3D 11 hardware, it is possible to access UAVs in pixel shaders. This opens up interesting possibilities such as A-buffer algorithms that allow a list of fragments to be created per pixel. To create a resource that can be used with a UAV, we need to add a D3D 11 bind unordered access flag at resource creation time. For our image processing example, we first render the scene into a render target texture. This image serves as the input to the compute shader. For the compute shader, there are two passes. One is blur Y CS, and one is blur X CS. It's necessary to copy the compute shader output to a texture from a texture so that the subsequent compute shader or pixel shader can be used on the intermediate data. For this example, we'll dispatch a set of dimx by 1 groups. The group size is also defined in the compute shader. We have a number of calls here which set up our resources, namely CS set shader resources, which bind memory resources of a buffer or texture type, CS set constant buffers, which bind read-only buffers and store data that does not change during the shader execution, CS set samplers, which bind samplers that control how the actual textures themselves are accessed, CS set UA unordered access views, which binds unordered access views, and finally CS set shader, which binds the compute shader. Afterwards, we restore the original render target for the final image. We then take the output from the compute shader and apply a pixel shader to render it. For this example, we simply draw a quad to display the results in graphics. The code shown here is a simple vertex shader for displaying the quad. The code shown here is a simple pixel shader that applies a simple tone mapping operation and displays the output on the screen. Here we see the rolling box blur demo. In the screenshot, we have a radius of 0, which means it's effectively doing point sampling, and we achieve a frame rate here of 113 FPS. Note that the frame rate here doesn't change significantly, even though we're using a radius of 10. With a radius of 10, each sample in the output is now taking an area of 10 by 10, or 100 different samples, which all contribute to its output value. But our frame rate hasn't dropped significantly. Similarly, as we proceed, we can set the radius higher. In this case, we have a radius of 100, while still achieving 107 FPS. The rolling box filter has constant compute requirements and a constant number of memory reads and writes. Let's take a look now at a live demo of the rolling box blur. Here we see the image processing example of the rolling box blur filter running on a GPU. What we have here is a 3D model that's interacting with an environment map shown in the background. It's running on a GTX 480 GPU. Initially, we have the blur radius set to 0, but as you can see, we can tweak the blur radius. Here we have the blur radius set to 10. Despite the change in the blur radius, you can see that the frame rate hasn't changed significantly. We can further increase the blur radius. Here we split the blur radius up to about 50. Again, the frame rate hasn't changed significantly. We can further increase the blur rate, in this case going all the way up to 300. Now, 300 by 300 pixels are all contributing to every output pixel. But as you can see, because of our rolling box blur implementation, the frame rate remains roughly the same. Our next example is an n-body simulation. This program performs a parallel simulation of an n-body system of stars, such as an astrophysical simulation in which each body represents a galaxy or individual star. It simulates the evolution over time of the positions and velocities of a number of massive bodies that all influence each other via gravitational attraction. Because all the bodies interact with each other, there are order n squared interactions computed at each time step, basically at each frame. Hence, there's a lot of computation, and the problem is highly parallel, and thus amenable to and well suited to GPU direct compute shaders. This code shows the body-body interaction function. Basically, this function computes the gravitational attraction between two bodies at positions Bi and Bj. The mass of the bodies is stored in the W component. This function, gravitation, is the main gravitation function, computing the interaction between a body and all other bodies in the system. The other bodies are stored in shared memory, and basically this function loops through a tile with shared memory, computing the interaction between this body and the other bodies in the shared memory. This function here, compute body acceleration, computes the acceleration of the body with position myPos caused by the gravitational attraction of all other bodies in the simulation. As you can see, it loads in a tile of data into shared memory and calls the gravitation function in order to compute the interaction between the other elements inside the shared memory tile. This function here is the n-body update, which is the main entry point for the compute shader in the n-body simulation. It computes the total attraction on the body with position myPos caused by the gravitational attraction of all other bodies in the system. In our simulation, the compute shader runs and it outputs the updated positions to a UAV, which stores position and velocity of the particles. A geometry shader is then used to access this information, and it creates point sprites based on the final output of the compute shader. Two triangles are appended to a triangle stream and passed through the draw call. This image shows a screenshot of the n-body simulation. Let's take a look at a live demo of the n-body simulation. Here we see the n-body simulation running on a GTX 480. As you can see, the simulation is simulating 30,720 different bodies and their interaction via gravitational attraction. Here we're achieving 30 frames per second and running at approximately 500 gigaflops per second in our simulation. As you can see, the compute shader is calculating the gravitational attraction, and then the geometry shader is being used to draw the particular point sprites. The simulation is 3D, and we can pan around and look at the positions of different bodies. Our next example is an ocean simulation. In this example, we generate an ocean height field using a compute shader in order to compute an FFT. Our example synthesizes waves in frequency space based on a statistical model. A complex to real conversion on the FFT output converts the FFT output to a spatial domain, which is used to generate the height field. The screenshot shown here shows a wireframe interpretation of the height field generated by the FFT. The height field, or displacement map, is naturally tiled. The FFT helps generate a displacement map used later in the pixel shader. And the final result then is a more realistic simulation of ocean water and waves. This screenshot here shows the pixel shader then applied to the computed height field. Let's take a look at a demo of the ocean simulation running on the GPU. This demo shows the ocean wave simulation using FFTs computed on the GPU. In the demo, the FFTs are computed in a compute shader to produce a displacement map. The pixel shader then uses this displacement map information and performs a pixel shading. In particular, the environment has been mapped onto the waves. Here we see the height field being interpreted via wireframe without the pixel shader running. Here again we see the pixel shader, where effects such as environment mapping have been added in, and so we can see the sky being reflected in the waves. This demo is running on a GTX 480 and is achieving 175 frames per second. In summary, the DirectX 11 compute shader offers many opportunities for offloading the CPU processing onto the GPU. Compute shaders enable more efficient algorithms. For instance, we saw how a rolling box filter, not possible on previous pixel shaders, could be implemented in a compute shader. Finally, we saw an example of how we can simulate particles with FFTs using the compute shader. Thank you very much.